Hello and welcome back to another video as we continue our discussion about chemistry topics. And in this one we are going to be looking at the topic of oxidation and reduction. If you remember from a video quite a while ago in a previous unit, we were talking about different types of reactions. And oxidation and reduction, they go hand in hand. This is another type of reaction where you're going to see the transfer of electrons. That's how you know whether an oxidation reduction reaction has occurred. Is there a transfer of electrons? Well, how are we going to know whether there's a transfer of electrons? We are going to devise a system where you are going to assign values, oxidation values they're called, or oxidation states, oxidation numbers, to each of the atoms in the compounds or the elements in the reaction, and we're going to see if there's a change from the reaction side to the product side in those oxidation numbers for a particular element. If there's a change, that means there's been a transfer of electrons. Okay? So, stick with me. Let's move through this, and let's start by reading this together. It says silver tarnishes when it comes in contact with sulfur compounds in the air. Copper gets coated in beautiful green patina as it ages. Metal rusts and corrode. Minerals, ionic compounds are saying, found in ore can be decomposed with the use of electricity to produce pure metals and nonmetals. They're giving you examples of a bunch of different types of or different reactions that are oxidation reduction reactions. So all of these reactions are examples of oxidation and reduction. If you put those two words together, the RED from reduction and the OX from oxidation, and just combine those together, we're going to call this a redox reaction. They have to go together, by the way. If you've got oxidation, you have to have reduction. If you've got reduction, you have to have oxidation. So that's why we just combine the two words together, and we just refer to the combination as a redox reaction. Okay, so let's see what happens when you have a redox reaction by exploring the models that are offered to us. In this model here, we are told that these are redox reactions, oxidation and reduction both happening. We are told that these are redox reactions here, and then down here we have a set that are non-redox reactions. Okay, so I'm just letting you know that is what the model is, and now we're going to answer some of the questions. First of all, it says what two types of reactions are shown. We've got redox reactions and we've got non-redox reactions. And we're just going to try to figure out what the difference is between them so we can identify when we have a redox reaction. Examine the redox and non-redox reactions in Model 1. Is or are there any features in the redox reactions that would allow you to identify them as redox reactions? So let's look specifically up here and see if there's something going on that helps us understand whether a redox reaction is occurring. You may notice that in some redox reactions there are some ions that are involved, some charges that are involved. Doesn't mean there has to be charges on the different species, but sometimes there are. So you'll notice here that this zinc on the left side, the reactant side, has no charge on it. It's a neutral atom, an element of zinc. Over on the other side, it does have a charge, a +2 charge. Copper on the reactant side started with a charge, and then on the product side it has no charge. So maybe that's an indication when there's a change in these oxidation numbers, which we're going to start to assign and discover the rules for, maybe that's an indication of redox. Now that doesn't mean you're not going to see ions in a non-redox, as is the case down here. There are ions involved here as well. Okay? But what we're really looking for is there a change in the oxidation number? Is there a change from the reactant side to product side? Okay? So, for example, down here in G, there's an ion, Ba2+, it's in aqueous solution. Here's a hydroxide ion, also in aqueous solution. And when the reaction occurs, you have an ionic compound. Well, how is that ionic compound formed? It's because Ba has a 2+ charge, OH, the hydroxide ion, has a -1 charge, and you need 2 hydroxides to bond with the 1 barium to make a neutral compound. But notice, barium on this side has a 2+ charge, barium on this side has a 2+ charge. Or we're going to start calling those oxidation numbers. Over here, hydroxide is a -1. Here, hydroxide is a -1. So there's no change. But as I mentioned before, up here in the group of redox reactions, there is a charge, there is a change in the oxidation numbers. Zinc went from 0 to 2, copper went from 2 to 0. Okay? There is a connection between the oxidation numbers and the ion charges that are most commonly formed for those particular elements. Okay? So, are there changes? For redox, we might be able to summarize this by saying redox, there is a change in the oxidation number. Okay? So you may be wondering, well, how do we get these oxidation numbers? Are they just the ion charges? Yes, in some cases, and maybe a little more complicated that in other cases. So let's talk a little bit about how we find those oxidation numbers. The oxidation rules that you're going to use are simply man-made. It's just a system that is devised by scientists in order to do what? Track electrons. Remember, a redox reaction happens. Why does a redox reaction happen? It happens because there is a transfer of electrons. And if there is a transfer of electrons, that means we want to try to track those. We want to figure out if there is an actual transfer of electrons. Okay, so this system, the oxidation guidelines, oxidation number guidelines, is a system that we use just to see if electrons have moved from one atom to a different atom. And that's going to be obvious by looking at the oxidation numbers and see if there's a change. So here are the oxidation rules, and I believe I put these in the course as well in this particular unit. We just follow these rules to assign a number to each atom in the reaction. Rule number 1. It says the oxidation number of an atom in an elemental substance, meaning you just have an element all by itself. You just have copper. You just have iron. You just have chlorine, whatever. If it's all by itself and there's no charge on it, it's just a single atom for that element, then the oxidation number is 0. It's not written, there's no number up here, it's understood that it is just 0. Okay? And you're going to have to know that. It's not going to be given to you, you're just going to know that this element, this atom of an element, if it's all by itself, it's a 0 for the oxidation number. And if it's diatomic, like O2, actually Cl2 would be diatomic as well, okay? Then it's still 0. That's an element right there. That's just a lone element by itself. Even though it's a molecule of oxygen, it's not a compound with another element. It has an oxidation number of 0. Number 2, the oxidation number of a monatomic, that means just one atom, mono, one atom, ion, now it's charged, has a charge on it, is equal to the ion's charge. Remember I said it's kind of connected to the ion's charge. So if you had, instead of just plain neutral iron, you had Fe and it had a 2+ on it, then the oxidation number that we assign this Fe is the same as the charge on that ion. Okay? It's just that simple. If you've got that chloride ion, then the oxidation number for this chloride ion would be a -1. Rule number 3, oxidation numbers for common nonmetals are usually assigned as follows. In other words, what they're saying is there are going to be some elements that are always going to be fairly consistent, fairly constant as far as their oxidation number. And here they are. If you see a hydrogen, it is always going to have an oxidation number of +1 when it is combined with other nonmetals. Okay? It will have an oxidation number of -1 when it is combined with metals. Oxygen always is going to be a -2. Now I say always, but of course there are exceptions. So in most compounds it is a -2. All right? There are exceptions and those will appear, and you can read about those down here in the exceptions. Okay? Halogens, that is the group with chlorine, fluorine, bromine, they are always going to be -1. -1 for fluorine, -1 for other halogens, except when combined with oxygen or other halogens. In that case, there is an exception. Okay? But for the most part, hydrogen is going to have a +1, oxygen -2, halogens are -1. There is some consistency there that is going to help you when you're finding the oxidation numbers of other elements in compounds with these three: hydrogen, oxygen, and the halogens. 4. The sum of oxidation numbers of all the atoms in a molecule or polyatomic ion equals the charge on the molecule or ion. Let me give you an example. I'm going to give you two examples actually. Okay? What they're saying is, in this polyatomic ion, all of the oxidation numbers have to add up to the charge on this polyatomic ion. This charge belongs to the entire group here, the S and the 4 O's. So that means the oxidation number of the S and the oxidation number times 4, this is for the oxygen here, the sulfur oxidation number and the oxygen oxidation number times 4 has to equal this charge right there of -2. And if we know oxygen, it's given to us, usually it's -2. If we know oxygen, S plus 4 times -2 has to equal -2. Well, hopefully you see that you can solve for the oxidation number of S there. Okay? Likewise, if you've got water over here, that means you've got 2 hydrogens, 2 times the oxidation number of hydrogen, plus the 1 oxygen has to add up to what? There's no charge on this water. It's a neutral compound, so it has to add up to 0. Well, if you know one of these, you can find the other one. Now actually, both of them are usually pretty common. We discovered that up here in the rule 3 of our oxidation numbers. But let's say we know, okay, oxygen is a -2. That means I could find the hydrogen if I needed to by taking this equation and solving for H right there. And that would give me the oxidation number of H. Okay? So that's how you find all the oxidation numbers of each atom of all the elements in a reaction, and then we compare left side, reactant side, to right side, product side, and see if there is a change in any atom's oxidation number. If there is a change, that tells us that there's been a transfer of electrons, and it is a redox reaction. So, right here, let's practice this a little bit. In the space under each reaction in Model 1, write the oxidation number for every atom. Divide the work amongst your group. If you're working with a group, that's great. Otherwise, we'll do them together here. I'll do a few of them. An example is shown here. So what they're doing is, here we've got elemental iron. Oxidation number is 0. Okay? Don't worry about the 4 outside here. That's telling us we got 4 of those. But each iron has an oxidation number of 0. Okay? Don't worry about the coefficients when you're dealing with these oxidation numbers. O2, that also is an element. There are 2 oxygens in that molecule, so we're going to put 0, 0 for each of the atoms in that particular molecule. Over on the other side, we've got Fe2O3. This compound is a result of an ionic compound. Ions must have been formed in order for these now to be bonded. Well, iron 2, there are 2 irons combined with 3 oxygens. That must mean that the ion for iron is a 3+, and the oxygen is a 2-, because they're combining in a ratio of 2 to 3 to get a neutral compound. Alright? So, but oxygen we know is always -2, so we're going to put -2, -2, -2. Why 3 of them? Because there are 3 atoms in that particular compound. And if there are 3 of them, I'm just going to show you how we could use that final rule in order to find iron if we don't know it. Well, iron, there are 2 of them. And oxygen, there are 3 of them. And it has to equal up to what? 0, because this is a neutral compound. 0. So oxygen, I know, is a -2, always according to the rule. Iron is not always the same, by the way, so we might have to discover this. That's why we're doing it right now. I'm going to drop in -2 in here, so I have 2 times the iron plus 3 times 2, which is -6. And I'm going to solve this for the iron. And it does come out, when I divide this both sides by 2, it does come out where iron, in this case, is going to give me an oxidation number of -3. So that, sorry, plus 3 here. I should add in 6 to both sides there, okay? Divide by 2. Sorry about that. And then this gives me +3 for my oxidation number for each atom of the iron. So I'm going to put 2 +3s underneath there. Now, what are we looking for? We're looking for a change. Iron went from 0 to +3. Change. Oxygen went from 0 to -2. Change. This is definitely an example of a redox reaction. Okay? So I'm going to encourage you to come back up here, back up to Model 1, and let's spend a little time. You just have to do A, B, C, and D. Those are the only ones that are redox reactions according to this model. And let's assign some oxidation numbers. Zinc, it's an element, 0. Copper, it's an ion, a monatomic ion. It's the same, oxidation number is the same as the charge on it. Over here on the other side, zinc, monatomic ion, the oxidation number is the same as the charge. Copper, element, no charge on it, 0. See how easy that is? Okay, iodide has a charge on it of -1. Again, ignore the coefficients when you're doing this. Iodide, -1. Here, we're going to come back to that in a little bit. This iodine, it's not an ion, it's neutral, and it's just an element. It's a molecule, yes, but you're going to have 0 over here. If you want to put it twice, that's fine, because there are 2 atoms there, that's fine. Okay, let's talk about the other 2 here. Here you have a polyatomic ion. It's a compound with a charge on it, okay? And let's figure out what the S is going to be here. You've got 2 S's plus 8 oxygens have to add up to the charge on this of -2. And I know oxygen is always a -2, so 2 times S plus 8 times -2 has to add up to -2. And that would give us the charge on the S. So it's -16, add 16, that's going to give me 14 on that side, divide by 2, that's 7. So in this case, each S is a 7, and all 8 of the oxygens are -2. Okay? Over here, we're going to do exactly the same thing. Ignore the coefficients. This time we've got 1 S plus the 4 oxygens has to add up to the charge here of -2. So each oxygen is -2. So in this case, I've got -8. I add 8 to the other side, gives me 6. Divide by, no, just 1, so I don't have to divide, so it's just going to be a 6. So in this case, the S is 6. Each oxygen is still -2. So let's see, is there a change? By the way, there has to be a change in oxidation numbers for 2 different elements, at least, in order for there to be a redox reaction. Because if there's a transfer of electrons, something is losing electrons and something is gaining electrons. So there has to be 2 elements that their oxidation number is changing. One whose oxidation number is going up and the other whose oxidation number is going down. Keep that in mind. So in this case, look what iodine does. Iodine goes from -1 and it goes to 0. Its oxidation number actually goes up, -1 up to 0. Sulfur, its oxidation number goes from 7 down to 6. Its oxidation number is reduced. Reduction, reduced, okay? So oxidation means that your oxidation number actually goes up. So this is your oxidation that is happening. Down here, this is the reduction part that is happening. Reduction means the oxidation number is reduced. Oxidation means the oxidation number goes up. Okay? And we'll talk about the electrons in just a second here. Let's come over here. Iron, that's an element, 0. Oxygen, 2. O2, that's an element, 0. In a compound now, we've got ionic compound. Oxygen is always a -2, so each of these are -2, and there are 3 of them, so that's a -6. So the iron over here, if you've got 2 of them, each of these should be a +3 to get a neutral compound. Ignore these coefficients. Don't worry about the coefficients. So what's happening here? Iron is going from 0 up to 3. That must be oxidation. Oxygen is going from 0 down to -2. That must be your reduction part of the reaction. Okay? Here, you've got hydrogen. It has an ion charge on it, and it's going to be the same as its oxidation number, so this is a +1. Here, you've got another monatomic ion, so that's a +2. I'm just going to do the easy ones first. Here, this is a +3, and now let's go and do the compounds or polyatomic ions. Each oxygen here is a -2. 1, 2, 3, 4 of them. That's -8. And with the manganese, I have to add the manganese there, whatever its oxidation number is, and get a -1. So this must be a +7. If I come over here, oxygen, each oxygen is -2. And there are 4 of them, so that's -4. Sorry, there's 2 of them, so that's -4. And it has to add up to 0. There's no charge up here. It has to add up to 0. So this manganese must be a +4. Water, each oxygen is -2, and ignore that coefficient. The hydrogens must add up so that with the oxygen to give me a 0, so each of these must be a +1 because there are 2 of them. Okay? So let's see where the changes happen. Hydrogen did not change. +1 on the left side, +1 on the right side. Let's look at oxygen. -2, -2. Oxygen didn't change. So it leaves us with the other 2 elements. Manganese went from +7 and it went down to +4. So this is your reduction. Iron is +2 and it went up to +3. There's your oxidation. Okay? So what have we discovered? Oxidation, that part of the reaction, happens when the oxidation number goes up. If it becomes more positive, tell me what's happening to the electrons. Well, electrons are negatively charged, so it must be losing electrons. Okay? Losing electrons. So oxidation means loss of electrons. Reduction, if the number is becoming smaller, how does it do that? You can't lose protons. You can't lose protons. You can't lose positive charges, the protons. You can only gain or lose the electrons in these reactions. So to go from +7 down to 4, it must have lost. So reduction is, sorry, it must have gained electrons. Okay? Because the charge went down by gaining more and more negative electrons. Okay? So oxidation is the losing of electrons, reduction is the gaining of electrons. Okay? Here's just one way that you can always remember that, by the way. If you remember oil rig, all right, the 2 words there, oil rig, this would stand for oxidation is losing. O-I-L, oxidation is losing. Rig, reduction is gaining, and that refers to electrons. So oxidation is losing electrons. Reduction is gaining electrons. If you just remember the 2 words, oil rig, that will help you. Okay? All right, so we did all of those oxidation numbers, and now it says here in step 4, identify any elements that change oxidation numbers, and we already did that. Connect the starting and ending oxidation numbers with a line, and I did that for you. Here's a key point. Based on the oxidation number analysis you just performed for the reactions in Model 1, are there any features of the redox reactions that would allow you to identify them as redox reactions? In other words, what are you looking for to identify if you have a redox reaction? And it's real simple. If you have a change in oxidation numbers. So again, as mentioned, if one species, one particular element, if its oxidation number goes up, as is the case here with this iron, that means it is being oxidized. And if another species, another element, its oxidation number is going down, as is with the oxygen here, both have to happen. You can't have one without the other. Both are happening if there's changes in oxidation numbers for two different elements. One whose oxidation number is going up, one whose oxidation number is going down. You have a redox reaction. Okay? So there has to be change in oxidation numbers for two elements where one goes up and the other goes down. Okay? Identify the following reactions as either redox or non-redox using oxidation numbers as evidence. So that's all we have to do. We just look and see if there's changes in oxidation numbers. Let's assign them. Here we have lead nitrate. We've got sodium iodide, and a reaction occurs. This is a double displacement, by the way. These are two ionic compounds. The lead and the sodium are going to switch places. Notice now the lead is with the iodide, the sodium is with the nitrate. Okay? So let's assign some oxidation numbers. I'm going to assign each one here, and it may get a little complicated here because you're looking at this and saying, well, I know oxygen, but I don't know two of these in this compound. In this case, what we're going to do is we're going to use the nitrate ion charge to help us find the lead. Well, the nitrate ion charge for that polyatomic ion, maybe you want to look back at a list of polyatomic ions, common polyatomic ions, is a -1, and you've got two of them. So each nitrate is a -1, and there are two of them. Now this is for the whole group, not for the individual nitrogen or the oxygen. I'm going to deal with those in a second. Each nitrate is a -1. Okay? The lead then, in order to make a neutral compound, must have an oxidation number of +2. This must be lead 2 nitrate. Sodium iodide. Iodine is a halogen, and it is always going to be a -1. That means sodium must be a +1. Ignore the coefficients. Let's come over here. Iodine, the iodide ion here, is always going to be a -1. So -1, -1 for both of those. And that must mean that lead is going to be a +2. Okay? Sodium nitrate, again, the nitrate, this polyatomic ion, the whole thing is a -1. I'm sorry, and there's just one of them. And that must mean sodium is a +1. Now I could break down it into nitrogen and oxygen, but we're going to see no change in oxidation numbers. Lead is +2 on both sides. Sodium is +1 on both sides. The iodine is -1 on both sides, and so on and so on. This is a non-redox because there is no transfer of electrons as indicated by no change in oxidation numbers. Over here, let's start with the easy one. Elements. H2, oxidation number of 0. Put 2 zeros there if you want. Oxygen, element, 2 zeros if you want for each atom. Here, H2O, oxygen is always a -2 in a compound, and that means for this to be a neutral compound, have a total charge of 0, the hydrogen has to be each +1. Okay? So, change? Definitely. Hydrogen went from +1 down to 0, there's your reduction, and oxygen is going from -2 up to 0, there's your oxidation. So hydrogen is going to be gaining electrons, oxygen is losing electrons, and that's why you've got the change in oxidation numbers. CH4 and oxygen, this is a combustion, by the way, and this one up here was decomposition. This one up here is combustion. And the one that we had up here, this was a double displacement. Just a little review from previous material. Okay, here we go. Element, oxygen, 0. Each of those are 0. Okay. Hydrogen with other nonmetals is going to be a -1. So we've got negative 1, negative 1, negative 1, negative 1. That means the carbon must be a plus 4. Okay? Here, water, oxygen is a negative 2. Each hydrogen must be a plus 1 to get a neutral compound. Oxygen is a negative 2 in compounds. There are 2 of them. That must mean the carbon must be a plus 4 to make that a neutral compound. Any changes? Yes, there are. Hydrogen is going from negative 1 to plus 1. So it is going up in, sorry, that should be a plus there, plus 1, so it is going up, so this is your oxidation. And oxygen is going from 0 to negative 2, it's going down, there's your reduction. HCl, Cl is a halogen, it's going to be a negative 1. That must mean hydrogen is a plus 1 to give you a neutral compound. And here we've got sodium and hydroxide. The hydroxide, by the way, you should recognize this as a polyatomic ion that would have a charge of negative 1. That must mean the sodium has a plus 1. But I'm also going to break down that hydroxide there. Okay, let's break this down a little bit. Oxygen is a negative 2, and hydrogen is going to be a plus 1. Do all of these add up to 0? Yes, they do. They have to add up to 0 because there's no charge on that compound there. Oxygen, we've done water before, so this is negative 2. Each of the hydrogens is plus 1. Sodium is a plus 1, and chloride ion is a negative 1. Halogens are always negative 1, so the sodium must be a plus 1. Okay? Changes. The change is going to be nowhere. We have no changes whatsoever. So this is a non-redox reaction. Okay? This reaction occurs, by the way, this is an acid-base neutralization. Acid and base are coming together to form a salt. An ionic compound is a salt, and water. That's what always happens with an acid-base neutralization. And this is simply just a double displacement reaction. Sodium and hydrogen are switching partners. Okay? All right. The process of oxidation and reduction can be thought of as a transfer of electrons from one atom to another. Thus, one atom gives up electrons and the other atom gains electrons. As a result of this process, the oxidation numbers of both atoms change. All redox reactions can be divided up into 2 reactions. Has to have both parts. An oxidation half reaction, that's half of it, that's part of the reaction is the oxidation part, and the other half of it is the reduction part. Okay? So let's kind of analyze it a little bit further, break it down a little bit further, and look at half reactions. Each redox reaction can be divided into the 2 parts. Just the oxidation part, we can just focus on that, and just the reduction part, we can just focus on that. So Model 2, this is exactly what we have. Here we've got the same 4 redox reactions as up in Model 1, but now we are showing just the oxidation part with this reaction and just the reduction part with the other reaction here. So notice this zinc is going from 0 to plus 2. Its oxidation number is going up. So zinc on the reactant side, zinc plus 2 on the product side, and we're trying to figure out how did that happen? Well, that's going to give us a clue. And over here, the copper is going from plus 2 to 0, so it's being reduced. So we have copper 2 plus as one of the reactants, and copper just atoms, neutral atoms, as one of the products. How did that happen? Well, we're given a clue here. Okay? So let's answer some of the questions. What does the E negative symbol represent? Well, those are your electrons. Okay? Look at the oxidation half reactions in Model 2. Which of the following types of particles may undergo oxidation? Circle all that apply. So what they're saying is, let's identify some things that commonly undergo oxidation. Remember, oxidation is the losing of electrons. I told you that already, but let's see if we can verify that up here. So we're saying what is commonly oxidized? Well, here we have neutral compound. Here we have anion. Here we have neutral, I shouldn't say neutral compound, there's a neutral element, neutral atom, and here we have a cation. So it looks like neutral atoms, or molecules even, neutral cations and anions can all undergo oxidation. Are electrons lost or gained by an atom during the process of oxidation? Well, in all cases, look what happens here. On the product side is where you see the electrons. That means they were produced, they were freed up, they were let go. If electrons appear on the product side, that means that they were let go from this zinc over here and are able to move to something else. So in all cases on the oxidation, look where the electrons are. Product, product, product. They are produced, meaning they are released and able to be transferred to something else. So in every case here, are electrons lost or gained? They are lost. And you're always going to see them on the product side for oxidation. Okay? The electrons on the product side for oxidation. Does the oxidation number of an atom involved in the process of an oxidation increase or decrease? Well, it's going from 0 to +2. From -1 to 0. From 0 to +3. +2 to +3. Always for oxidation, the oxidation number is going to increase. Look at the examples of reduction. Well, now you can figure out that kind of the opposite is going to happen for reduction. So let's see what kind of species are often reduced. Here we have cation, polyatomic anion, neutral molecule or element, and here we have your cation, your polyatomic anion. Okay? So anion, neutral, and cation. In all cases, any of these can go through reduction. So that's not going to be the key in whether something is reduced or oxidized. The key is follow the oxidation numbers. In this case, are electrons lost or gained? Well, for reduction is the gaining of electrons because the oxidation number goes down. So reduction, oxidation number goes down. How does it do that? By gaining negative electrons. Okay? Does the oxidation number, we just said this, it's going to decrease. Okay? Reduction, oxidation number is reduced, reduction. Consider the word reduction. In reduction half reactions, what is reduced? And that would be the oxidation number. Okay? The assigned oxidation number is reduced. And I'm also going to look and remind you here that in oxidation the electrons are produced, so in reduction the electrons are part of the reaction. They are kind of absorbed, they are gained, they are brought into the reaction here. Okay? So look at the difference where the electrons are placed in these half reactions. These two half reactions here. For the oxidation, it is produced, and then for reduction, those electrons are absorbed and part of the reaction to produce whatever the product is in the reduction reaction. Oxidation occurs when atoms lose. Oxidation is losing, oil. Reduction occurs when atoms gain electrons, Rig. Reduction is gaining electrons. These two processes always occur together, always, always, always. In other words, you can't just lose electrons and just have them go off somewhere by themselves. Okay? They must be grabbed by some other atom. There's a transfer from one to the other. And you can't just grab electrons from somewhere out in space. That's not where they hang out. They must be taken from some other atom. So here's another way for you to remember. I gave you oil, Rig. Another way is to go and say Leo, meaning like Leo the lion, says grr, like a lion growls, right? So Leo says grr. So Leo stands for loss of electrons is oxidation, L-E-O. Grr, the growl there, is G-E-R, gain of electrons is reduction. So whatever you want to use, whichever helps you, wonderful. Number 11, consider the incomplete half reactions below. Use oxidation numbers to identify the reactions below as oxidation and reduction, and then we're going to place the correct number of electrons on the appropriate side of the reaction to complete the equation. So let's first assign oxidation numbers, and we're going to identify if it is oxidation or reduction. These are just half reactions. These are not complete reactions. These are not complete redox reactions. It's only half. It's only going to be oxidation or only going to be reduction. They're not showing you the other half of this particular redox reaction. Okay? Okay. Iodine, neutral, so each is 0. And over here you have an iodide ion, and it's going to be a -1. So in this half reaction, your oxidation numbers are going from 0 down to -1. That is reduction. And anytime you have reduction, that means you are gaining electrons because the oxidation number is becoming more and more negative. It's going down. You're gaining negative values. So you're going to place the electrons on this side. They're being picked up. They're being gained. Well, how many exactly? Well, in this case, I am going to consider now the coefficients. You have 2 iodine atoms over here that are bonded together. They get broken apart and produce 2 separate ions, iodide ions. They're separated here, but 2 of them. That's why the 2 is a big coefficient there. So I'm actually going to put 2 here. So I need to have 2 electrons gained in order to produce the 2 different charged ions here. These are different and separate. So I'm going to put a big 2 over here to make sure that the charges are balanced. I can check this. It's real easy. The total charge over on this side is 0 without the electrons. The total charge over here is going to be a -1 and another -1 because there are 2 separate ions. So 2 -1s. In order to balance the charge, because you can't gain or you can't lose or destroy electrons. They're just going to be transferred. So if this side over here is a total of 0, and this side over here is a -2, how am I going to balance the charge by introducing electrons? So I hope it's obvious then. I'm going to add and introduce 2 negatives over on this side, and I do that by adding the 2 negative electrons. So that's another way to determine whether the electrons are going to go on the reactant side or the product side, is to try to balance the charge on both sides. Compare reactant side and product side. Make sure the total charge on the reactant side is equal to the total charge on the product side. So in this case, over here on the reactant side, I have a total of 2 negative because of the 2 electrons, and on this side I have now 2 negatives as well. Charges are balanced. Here, this is chromium 2+. It's a monatomic ion, so its oxidation number is +2. Here, +3. What's happening? Oxidation number is going up. So this is oxidation. It's going up because it's losing negative electrons. How many? Well, the difference is it went from 2 to 3. It only went up by 1, so it must have lost 1 electron. Okay? Here, 0, and then it goes to a +2. Remember, this is only half of the reaction. What half is it? It's going from 0 up to 2. Gaining in its oxidation number means its oxidation. How far did it go up? It stepped up by 2. That means it must have lost 2 electrons. Again, let's check the charge. Over here, the total charge on the left side is 0. The total charge on the right side, well, I've got +2 and 2 times -1. So +2 and -2, this is 0 over here as well. So all of this is 0 if I add up all the charges. And if I add up all the charges on the reactant side, both sides are 0. The charges balance. They have to. You have to balance the charges in a redox reaction. Here, let's do the water first. It's easiest. -2 and each of these is a +1. And oxygen is a -2, so each of these is a -2, -2, and they have to add up. This whole thing, this whole polyatomic ion has to add up to -1, the charge right there. So if I got -4 already, then the chlorine must be a +3 to give me a total of -1 there. Over here, now I've got ClO3. Each of these is a -2. That gives me -6, plus the chlorine has to give me a -1, so this must be a +5. You can see the change there. And each hydrogen is a +1. Hydrogen didn't change. Sorry, that's a plus there. Hydrogen didn't change. Oxygen didn't change. It is the chlorine that is changing from +3 up to 5. Okay, we're only showing, in this case, oxidation. We're only showing the half reaction oxidation. The reduction part is not shown for this reaction. So it went up by 2. How did it do that? It went up 2 positive because it lost 2 negative electrons. Okay. Consider reaction A in Model 2. Reaction A in Model 2. Whoops, not that one. Let's go to the Model 2 here. Okay, this guy with the zinc and the copper. Okay? Consider that reaction. I'm just going to write it down. There we go. Show that the two half reactions can be added together to give the overall redox reaction. Consider how you would add two equations together in algebra. So let's go back to the half reactions. The half reactions were the zinc is going from 0 to +2, so it's going up. That's the oxidation. Oxidation part is zinc. Elemental zinc is going to turn into zinc 2+ ion by losing 2 electrons. And then the redox reaction is going to be the copper ion turning into neutral copper atom. And in this case, it has to do that by gaining 2 electrons. How do I know 2? Because the oxidation number is going from +2 to 0. And how do I know 2 for zinc? It's going from 0 up 2. So it has to be a transfer of 2 electrons. So all I do is I'm just going to add these together. And by the way, when I do add these together, I have to have the same number of electrons lost as the number gained. And I do in this case. 2 are lost, 2 are gained. That has to always be true before I add these two half reactions together. And now when I add these together, this is the condition that has to be true before you can add two half reactions together. You have to have the same number of electrons lost as the number that is gained. Once that's true, then you can add these together, and I just add all the reactants together on one side, and I add all the products together on the other side. And once I've done that, I really don't need the electrons anymore. They're just there to help me balance it, to make sure that I have the correct number lost and gained. And I really don't need those anymore. So you see that by looking at the half reactions and making sure that I have the same number of electrons lost and gained, it helps me get the final balanced reaction. In this case, it was really simple because the coefficients are all still just 1. But maybe we'll do one where the coefficients are a little bit different, and it shows us how to balance this. So we end up getting zinc plus copper ion producing zinc ion plus copper, which is exactly the original reaction that we were working with. Okay? So let's look at B then. B is going to be a little more involved, and we can see how making sure that we get the correct transfer of electrons, the number, is going to help us balance this. So let's take this guy right here. So we already have taken the reaction here, and it's been broken into the half reactions for us. Okay. By the way, how would you devise or how would you write the half reactions? You would look up here at the original equation, write down the oxidation numbers, and find out what is being oxidized. Write that part separately. What is being reduced? Write that part separately. And now what we want to do is we want to make sure are the number of electrons being lost and gained the same. They are 2 electrons lost, 2 electrons gained, so you can just add these together with no problem. You don't have to multiply one or the other of the half reactions by any numbers. You just add them together and you would have 2I negative and S2O8, 2 negative, producing the iodine and the sulfate ion. Okay, so that one's not very hard either. Let's take this one. This one actually is a little more interesting for us. We have our half reactions here, and let's write these down and work through this. Fe, sorry, here we go. I'm sorry, model 2. So we've got Fe turning into Fe3 plus, okay? And then we have the O2 turned into 2O negative. Okay. All right. So here's what we have. First of all, let's make sure each half reaction is balanced. There's one Fe on the right side, or sorry, the left side, one Fe on the right side. Okay? Fe's are balanced. Let's look down here. Are the oxygens balanced? I've got 2 oxygens here on the left side. Oh, I only got 1 here, so I got to put a 2 in front of this. Okay? Now I consider the electrons. How many electrons are gained or lost in these 2 half reactions? Well, Fe is going from 0 to plus 3. How did that happen? It lost 3 electrons. Oxygen is going from 0 to negative 2. Well, how did that happen? How did each oxygen go from 0 to negative 2? It gained 2 electrons each. Well, wait a second here. You can't lose 3 electrons and then gain only 2 electrons. That third electron is just where? Where to go? It's out there by itself? It never happens. So we have to account for that somehow. We have to have the same number of electrons gained as lost. So how do we do that? We have to multiply one equation or both half reactions by numbers to make sure we have the same number of electrons gained as lost. So if you've got 3 lost here, 2 gained, really we have to multiply the first equation, everything by 2, and the second equation, everything by 3, to get our least common multiple, basically. So I'm going to have 2 times 2, and then the 3 times 2 makes us a 6. And I'm going to multiply everything here by 3. 3, make this a 6, and this is going to be a 6 as well. Okay? Now, do I have the same number of electrons lost as gained? Yes, 6 each. Now I can add these together and cancel my electrons. Now I have the correct coefficients that balance my reaction. So it's 2Fe plus 3O2 producing 2 Fe3 plus ions and 6 O2 negative ions. I don't need the electrons in my final equation anymore once I have used them to balance the charges, to balance the transfer of electrons. And balancing that transfer of electrons also gives me the correct coefficients to balance my other elements. Okay, let's check. I have 2 irons on both sides? Yes. I've got 6 oxygens on both sides? Yes. 3 times 2 and 6 oxygen ions there. It's a great way to balance a redox reaction. So the same number of electrons that are lost during an oxidation must be gained by atoms during their reduction. Show how the half reactions for reactions C and D can be added together to get the overall redox reaction shown. So I just showed you C. This was actually C right here. Let's do D together just for a little more practice. Okay. So we have F2 turning into F3. And we got the MnO4 negative turning to MnO2, and we've got it in a looks like an acidic solution because you got the H plus there. Okay, so MnO4 and MnO2. Okay. and this was with hydrogen and producing some water there as well. Okay? So in these reactions, you have our two half reactions. Those are given to us. And let's figure out, first of all, the number of electrons that are gained and lost. I'm just going to pretend like we didn't see these numbers here. We don't know the number of electrons. Let's figure it out ourselves. All right? So here, iron is going from 2 plus to 3 plus. So its oxidation number changed by 1. It went up 1. That means it must have lost 1 electron. Just 1. 1 per atom of iron. Down here, what is happening? Well, let's write in some oxidation numbers. The H plus is going to be an H plus on this side as well, because this is plus 1, plus 1. Remember, oxygen is negative 2. Here, oxygens are negative 2. There are 4 of them there. And those 4 times negative 2 there, that's a negative 8. Has to add with the manganese to give me a negative 1, so this must be a plus 7. I think we did these oxidation numbers earlier, but that's okay. Good practice here. Each of these are negative 2. Has a negative 4 now with the manganese to add up to 0, so it should be a plus 4. So it is, in this half reaction, it is the manganese, and look what happens here. It's going from plus 7 to plus 4. It's going down by 3, so it must have picked up 3 negative electrons. Well, again, you can't lose 1 and then pick up 3. Where did it get those other 2 that picked up from? Can't happen. So we have to balance this by balancing the electrons. You are going to take one or both of these half reactions and multiply them by factors to make sure that you have the same number of electrons lost as gained. So the easiest way to do this is, I just want to multiply the first equation by 3. And that would make 3 electrons lost, 3 electrons gained. Now I can add my equations together. Actually, I would also check first that my elements are balanced. I should have done that first. In this equation, I had originally, before I multiplied by 3, I had 1 iron and 1 iron. Those were balanced. Down here, I should have really balanced my elements first. I had 1 oxygen here. I've got 2 on this side, so I should really double this. Manganese, I got 1 on both sides. Oxygen, I've got 2 and got 2 here and 1 more there. That's 3 and 4 on that side. I'm going to have to double this. Water to give me 2 oxygens and another 2. That's 4 to balance with the 4 oxygens. That now gives me 4 hydrogens. Well, that's okay. I can take care of that with my 4 hydrogens there. Okay. Now I have all the elements balanced. Then after balancing all the elements, I really should then look at the electrons, which now I can do. So I need 3 electrons lost, 3 electrons gained. I multiply everything in this first equation by 3 so that I have the same number lost and gained. I didn't have to multiply the second equation by something because I already have 3 electrons that are being gained to match the 3 that are being lost up here. Okay? So now that I have my elements balanced and my charges are balanced, I don't need these electrons in my final equation, and I can add these together to get my final balanced equation here. Just like this. Let's check. 3 irons on both sides, 4 hydrogens on both sides, a manganese on both sides, and 4 oxygens on both sides. There's 2 oxygens there, plus 3. And are the total charges on both sides the same? They should be. The total charge on this left side is 4 times plus 1, so it's a plus 4. This has a negative on it. There's no coefficient, so it's just a negative 1. And then 3 times negative 2, so it's going to be plus 6. This total charge over here is going to be 9. Over here, this is neutral, so that's 0. This is neutral, so that's 0. And then we got 3 times 3 plus 9. Look at that. Plus 9 on both sides. The total charge on both sides match up. They have to in a redox reaction. Okay? All right, are electrons conserved in redox reactions? Yes, 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 yes. Same lost as gained. Electrons can't just go off into oblivion, nor can they just be picked up out of space. Okay? When iron is exposed to oxygen, it forms rust as described by the following equation. In this reaction, oxygen is acting as the oxidizing agent. Oxidizing agent, that's a new term. Well, let's see what that means. We are told that oxygen is the oxidizing agent. Okay? What element was oxidized in the reaction above? This is a bit of an extension, so stick with me here. Well, let's look at the oxidation numbers. Iron originally is 0 because it's just an element. And then oxygen is also 0 because it's an element. Over on this side, each oxygen is -2. I'm not going to write it 3 times. Each one of those 3 is -2. And the iron then, if this is going to be a -6, this would have to be a +3 for each of the irons to give you a neutral compound. So iron is the one whose oxidation number is going up. Oxidation here in this case is the iron turning into the iron ion in the compound, the +3. It would be in a compound, but I'm just going to write it separately. It is the oxygen that is actually being reduced here. The oxygen is going from 0, and then in a compound, it is an oxygen ion. Each of them are 2 negative. Okay, this is an ionic compound right here. So wait a second, why is the oxygen called the oxidizing agent if it is being reduced? Well, it's just a term. You just have to realize this agent word right here is going to alter a little bit the significance or the meaning of what we mean, what we're talking about here when we're talking about oxidizing an agent. So think of it about it this way. The element that is being oxidized is actually the iron. Okay? Oxygen is considered the oxidizing agent. Agent is the key word here in this reaction. Consider the purpose of an insurance agent or real estate agent. So here's what I use to explain it. When you see the word agent, the agent is not the one doing the action. The agent is somebody who helps you do the action. So if I say oxidizing agent, an oxidizing agent helps somebody else, helps another element be oxidized. Okay? It is not being oxidized itself. So when we see the word agent, it means it is helping somebody else do this particular action, whatever the action is. So a reducing agent is going to help another element be reduced. Okay? An oxidizing agent is actually reduced, and a reducing agent is actually oxidized. By being reduced, it helps something else be oxidized. By being oxidized, it helps something else be reduced. So it's a little confusing when they throw the word agent in there. Okay? But it's not crucial. It's just an extension. It's a little added bonus as we're talking about redox reactions. The main point here that you need to understand is that for all redox reactions, there's a transfer of electrons. One species is going to gain electrons, one is going to lose electrons. Oxidation is the losing of electrons, reduction is the gaining of electrons, and in order to balance a redox reaction, every element has to be balanced, the number of elements has to be balanced in there, and the charges have to be balanced. The number of electrons lost and gained have to be balanced. Okay? Oxidation reduction reactions are everywhere. And now in the next videos, we're going to be talking about more of them and as they apply to batteries, which you guys, we use all the time, every single day. So we're getting into some really neat stuff as we see how all of the different topics in chemistry are being pulled together in these last few units. Okay? All right, we will see you in the upcoming videos.